current expression, it becomes IES exponential Q into VEB by KT minus 1, the emitter base effect, minus alpha I, some proportionality factor, ICS exponential Q into VCB by KT minus 1, the collector base one. Proportionality factor, I'm just coming. And similarly, the collector current ICN plus ICI, where the proportionality factor comes first, normal mode IES into exponential VEB term minus 1 minus ICS exponential Q into VCB by KT minus 1. So if you look carefully, there are two proportionality factors, because whatever is a normal mode of operation, in case of a emitter current, since emitter is always at the left, so after normal mode of operation, whatever is being achieved from this side, from the reverse active mode, the proportionality factor is multiplied, because that depends on the reverse flow. Similarly, when we are talking about the collector current is usually belong to the reverse active mode, क्योंकि हम collector में सारे electrons collect करते हैं. So that's why the proportionality factor is attached with the IES term, not with the ICS term, because IC belongs to the normal direction of the output. Whatever is actually coming from this side on the reverse active mode, that proportionality factor comes, because definitely whenever a transistor is operating it with a certain very minute duration of time, the switching happens, there is always certain proportionality factor you have to take into account, because 100% contribution cannot be achieved with a sudden reversal of the charges. Remember, the flow of charges we are considering. So even if you look in a practical example, our normal ceiling fan in all our houses, whenever you switch off the switch for the fan, or you changes the regulator button, fan doesn't immediately stop, or fan doesn't immediately go to the high speed. What is the reason? The reason is the storing of the charges, and those charges require minimum amount of time to lagging behind. That charge delay time, because whatever you can do, previously we have in a few classes earlier we have seen the charge response time, how it behaves, and nowhere you can find the output is a sharp. The output is always a delayed transition, and due to that delayed transition, certain proportionality factor you have to taken into account, that it cannot be completely switched into the reverse active mode. Few charges of the previous mode always remain. So that's why this proportionality factor alpha I and alpha n comes. And very surprisingly, in the inverted mode it is alpha I, and in the normal mode it is alpha n, it is denoted. There are many other forms to write it down, those charges and each and everything. So the other forms are IE equals to, I mean, if you recall the solid state devices classes, in terms of the excess carrier distribution, those are the different forms of analysis. Don't worry, you have to understand the expressions. But you don't have to mug up, because all those expressions will be given, but you have to be quite apt at what moment what equations you have to use. So IE equals to IES delta P by Pn minus alpha into ICS delta PC by Pn, and the I naught reverse saturation currents is alpha n into IES into delta PC by Pn minus IES into delta PE by Pn. I'm sorry, this must be IC, where the alpha n, or alpha I, the proportionality factor which we are talking, those are also defined as recombination lifetime by the transition time plus recombination lifetime. Similarly for alpha I, the recombination lifetime by the transition time plus, or mean carrier lifetime plus recombination lifetime. Correspondingly, the IES and ICS, those are also defined. Qn into 1 by tau n plus 1 by tau Pn. ICS QI 1 by tau Ti plus 1 by tau Pi, where Qn equals to Qn into delta P by Pn, Qi equals to Q of I delta Pc by Pn. Different forms in terms of the excess carriers that we have tried to configure here. The base current in a normal mode supports recombination and is given by, because every time we are deciding about the collected current and the emitter current, so little bit description about the base current as well. Qn by tau Pn depend on only the recombination lifetime, and hence base to collector current amplification factor is beta normal is ICN by IBN, alpha n by 1 minus alpha n, into tau equals to tau Pn by tau of Tn. One simple logical question comes. Here I have written the base to collector current amplification factor beta normal. Is there any beta I possible? Is there any beta?
No, sir. I don't think so.
Sorry, Swant, why you don't think so? The logic?
Sir,
Answer?
doping concentration of collector, sir.
समझा नहीं, थोड़ा elaborately समझाइए.
Sir, doping concentration of the collector is less than emitter. So the influx of the carriers will not be as much as compared to the forward
The influx of the
normal operation.
carriers will not be as much as that. Very good. And also a simple logic, I'm completely agree. And also a very simple thing. Whatever, if you recall, जितने भी inverted mode of operations थे, all were defined it with a. So even if you dope somehow the collector with a good amount of doping concentration, even in that case, suppose your mathematical equations will come, negative amplification factor doesn't have any meaning. If it is a plus 10 plus 100, then there is an amplification. So yes, that's why beta I is not possible. Somebody, Hakuruva Praveen, please. Praveen Kumar, you have raised your hand, please. सोते हाथ लग गया, don't worry. So if it is a negative term, so that's why negative amplification factor is not possible. So beta n equals to ICN by IBN, same concept, alpha by 1 minus alpha, or recombination lifetime by the carrier lifetime. So similarly, the IB has also two modes of current to be incorporated, IBN plus IBI, so Qn by tau Pn plus Qi by tau Pi. If we have to incorporate it, since it is a charge stored, and definitely charge stored cannot be a constant phenomena. Whatever we are doing till now, just we are deriving the equations, making it a constant one, but in a real life transistor, none of the charge storing or is time independent. It always be a time dependent phenomena, and since it is a time dependent phenomena, then corresponding the current cannot be a pure DC current. Hence the terminal currents can be represented as per the rate of change of stored charge in the time dependent form. Small ie equals to Qn by 1 by tau Tn plus 1 by tau Pn minus Qi by tau Ti plus dqn dt. IC Qn by tau Tn minus Qi 1 by tau Ti plus tau Pi minus dqi by dt, and IB Qn by tau Pn plus Qi by tau Pi dqn dt plus dqi by dt. So whenever there is a time dependency term, then correspondingly this time rate of change of stored charge comes into the play, and it cannot be assured a pure DC current to be ensured. So that gives a mathematical analysis of the first part of the first section, that is the charge control analysis. So if we can take in terms of the charge, then how does it look like? There is another model which we are going to take care of very quickly, that is known as the Gammel-Poon model. Why it is required? Gammel-Poon model, or there is another name also, Ebers-Moll model. In some of the book, मुझे नहीं याद आ रहा है, Boylston and Neshelski's book में it is in the Ebers-Moll model, which runs into the problems if a high degree of accuracy is required. That's only charge control model is required. I mean, whenever we are going to analyze a charge control model, it is a very high degree of accuracy is required, which we may not have to do for 24 billion number of transistors when we are analyzing. So in a little less accuracy one, we can start with a Gamelpun model where the starting point is for typically graded doping profile in the base, there is a built-in electric field that causes the drift of the minority carriers in the same direction they are diffusing from the emitter to collector. What does it mean by one? Graded doping profile. To be very honest, हम लोग मान लेते हैं emitter is heavily doped, then it is base, then it is collector. But are we sure when we are doing an arbitrary growth and fabrication? Growth and fabrication, it's मतलब ये पूरे ट्रांजिस्टर जो है इस पूरे ट्रांजिस्टर का डिवाइस लेंथ कितना हो सकता है in the order? Any idea?
Some centimeters.
Nanometers.
Nanometers. Maximum in this L will be in the order of nanometer. And whenever in a fabrication process these transistors are made, it is impossible to fabricate a single nanometer transistor. Impossible. उस तरह से फोटोलिथोग्राफी या आपके जो मास्क से वो डिजाइन ही नहीं हो सकते हैं. It is impossible. So what happens? Usually एक silicon wafer अगर इतने माइक्रोमीटर और इतने सेंटीमीटर बाय इतने सेंटीमीटर के सिलिकॉन वेफर मैंने पहला दिन सॉलिड स्टेट क्लास के डिवाइसेस में दिखाया था. If we have to utilize the full silicon wafer of this some centimeter cross centimeter area, then usually what happens, certain 10,000 or even 20,000 number of transistors are fabricated at a time from this silicon wafer at a time. This kind of a fabrication is called batch fabrication or mass fabrication. So this tiny things we really can't know. This n plus is everywhere. That means in this entire width or entire length of the emitter only, not the transistor, the doping everywhere is same. Not at all possible. So doping also varies in a gradual manner. कहीं पे ज़्यादा उल्टा सीधा भी हो सकता है, कहीं पे ज़्यादा कहीं पे कम. So there will not be a uniform doping. Always there will be a graded doping. And if there is a graded doping, doping directly controls the generation of the electric field. Electric field doping के साथ directly related है और inversely proportional है.
Directly proportional.
Directly proportional. So correspondingly, there will be a fluctuation in the built-in electric field. If there is a fluctuation in the built-in electric field, minority carriers के drift motion always depends. Whereas the higher electric field, the drift of motion will be higher. Where less electric field, the motion of the electric field will be less. So in this drift of minority carriers in the same direction could be found, like they will be diffusing from emitter to collector. So there are many problems are there. So as the electric field aids the motion of minority carriers in the base, the current can be written as IEP equals to Q into A into mu P, P of Xn, carrier distribution, in multiplied by the electric field, minus QA into dP Xn by dxn. So electric field means the drift term, dP by dx is the diffusion term. The built-in electric field can be defined from the Einstein's equation. If you recall, E equals to minus d by mu into px. So Ex n equals to minus dn by mu n for the electrons, 1 by n of xn, the electron distribution, into the gradual variation of the electron, dn by dxn, minus kt by q, because from the Einstein's relation, d by mu equals to kt by q, minus kt by q into 1 by n, kt by q 1 by n xn into dn by dx. Similarly, the IEP qa into mu of p minus kt by q into 1 by n dn dxn minus q into a dp by dp dx, and minus q into a into dp by n, using the Einstein's equation p into dnxn plus n into dp by dxn. So IEP minus QA by dPn by dPxn, you just go through all the equations and solve correspondingly, or if you just interchange on the left hand side and right hand side, and after integration from 0 to WB, if you take the width of the base is 0 to WB or WB, and keeping in mind that the current IEP flowing from emitter to collector, conventional one, emitter to collector, is more or less constant in the narrow blaze. So you can write the final form of this IEP 0 to WB n into dx by q into dp equals to integration 0 to WB d by dxn, which is p into WB into n into WB, or p into n r into n. That's not a just a notation to represent. As we know, equilibrium Pn product, that is n into p into equals to ni square from the mass action law, changes to the non-equilibrium expression as p into n equals to ni square into e to the power en minus fp by kt, because when it comes to the non-equilibrium, now since we have considered whatever the distribution of the doping is gradual, is not uniform everywhere, so correspondingly there will be a non-equilibrium, क्योंकि कहीं पे भी less carrier, कहीं पे भी excess carriers, even within the small emitter, small base or small collector. So no longer the uniform or the equilibrium Fermi level concept it will come to the quasi Fermi level concept or non-equilibrium situation. So that's why this is En or EFN, whatever you like to say, Ni square e to the power EFN minus Fp by Kt equals to Ni square e to the power Qv by Kt. But the separation of Fermi levels is determined by the applied bias. Hence, applying equation 6 to equation 5, we can just write it down the final forms as P of WB into N of WB equals to Ni square into e to the power Q into VCB by Kt. And these are the carrier concentrations at this point, WB point, and this is the carrier concentration at the initial point when it is Ni square into e to the power QVE by Kt, because it is only applicable with the emitter to base voltage at this point. So finally the IEP can be written as I minus Q into A into dP by Ni square multiplied E into Q into VCB by Kt minus E into Q to the power VEB by Kt divided by integration 0 to WB n into dx. So that is just only the solving of different kind of equations. These equations are very good given in the Streetman Manager's book, where you can you can solve it very clearly. Although Streetman Manager's books was mostly dedicated for the solid state devices part, but here you can refer this Gamal-Poon model and the charge control analysis were very beautifully given in the Streetman Manager's book. So under normal active mode of operation, while we are designing, charge control analysis was very precise control of approach, as we have told, where Gamal-Poon model is a relatively generalized approach. So we don't take care here about the inverse active mode, only the normal active mode are fine. So under normal active mode of operation, the emitter hole current is finally designed by this one, and the due to hole, and the base electron current flowing back to the collector is given as IEN Q into A into Pn Ni square into e to the power Q into VEB by Kt minus QE. So this is another one where we have just give you an example or a very generalized example of the equations. I would urge you to solve this equations of the Gamal-Poon model from the very beginning, from where we have started, and then step to follow step by step the solving of all the equations, so that you can finally be comfortable where we are coming with this final set of equations of the equations 9a and 9b, where this terms are usually given. This qb term is given as base Gummel number, integrated majority carrier charge in the base available. QE is the emitter Gummel number, integrated majority charge in emitter. Advantages of the Gummel pool model: the currents are expressed in terms of net integrated charge in the base and emitter, and can easily be handled the non-uniform doping, which was not possible in case of a charge control analysis or any other analysis. And definitely, but one common thing is, in case of a charge control analysis as well as Gummel pool model or Ebers-Moll model, they all deal with the charges. They are not just defining in based of certain doping and other things. They define across the charges, and depending on the flow of charges, how actually the terminal currents IE, IB, IC are calculated. Previously, in a bipolar junction transistor, we have seen how different components of currents are going, but we never have calculated or mathematically estimated how the currents are flowing. That we have done, which is extremely required when we are doing with the amplifier application of a transistor. So those two are the different models we try to intend for. Coming into the next one, uh, a little advanced structure of the bipolar junction transistor, or rather than heterojunction bipolar transistor, which we would like to express. Fine. अभी तक जो transistor whatever we have discussed back to PN junction diode, which has three parts: emitter, base, and collector. Both the bases are connected. And what we know, that usually emitter is little heavily doped, base is p-type, collector is n-type, but obviously less doped with emitter. More or less, in case of a normal problems, we take it is of uniform doping. The n plus, the emitter is uniform doping, base and collector are also little uniform doping. But when you have studied, have you noticed anything? I mean, have you noticed about the material used? What kind of a semiconductor material is used in case of an emitter portion, base portion, and collector portion? Or while we are doing certain kind of a problem, have you noticed very practically what kind of a material we have used in these three portions? जितने भी हमने problems solve किए हैं, ये बात किए हैं,
Silicon only.
silicon only. Very fine. That means all are the uniform material we have used. My intention of asking this question is uniform material we have used for whether emitter, whether base, whether it's a collector. There is no variation in the material. Material variation से क्या होता है?
बैरियर
The
जंक्शन मतलब वो सब की वैल्यूज अलग अलग होगी,
किसकी वैल्यू अलग अलग होगी?
मतलब विथ की जो इलेक्ट्रिक फील्ड जनरेट
नहीं
होती
चला,
है
दोबारा कट गया, फिर से बताइए. किसकी?
इंट्रिंसिक फर्मी लेवल का वैल्यू अलग अलग हो जाएगा.
फर्मी लेवल नहीं, फर्मी लेवल का वैल्यू अलग होने से क्या होगा? एप्लीकेशन वाइज क्या
सर
चेंजेस?
बैरियर विथ, सर आवाज आ रही है सर?
हाँ
सर बैरियर विथ की वैल्यू अलग होगी, पोटेंशियल मतलब उनकी इलेक्ट्रिक फील्ड जो अंदर इंड्यूस होगा वो उसकी वैल्यू अलग होगी.
हाँ ठीक है, तुमने सब बता दिया, बेसिक एक टर्म छोड़ के.
sir, knee voltage will vary.
नी वोल्टेज क्या होता है?
Means like forward biasing or reverse biasing में जो
Sure, forward biasing, reverse biasing are in our hand. We are externally providing. How forward biasing, reverse biasing will change? We can change the material. Biasing is in our
but
hands.
like for
It's
silicon
batteries.
that is
But if the material is there, there is a practical limit of the biasing that we know from the manufacturer's date sheet, and we
सर
can change.
उनकी ब्रेकिंग पॉइंट भी अलग अलग होंगे,
Breaking क्या point होता है?
मतलब
गाड़ी
जब तक वो रिवर्स बायस में काम कर सकते हैं जितना.
break down voltage, that is
हाँ
going to break
वही
it,
सर.
whatever. नहीं, और कुछ एक बेसिक टर्म मिस कर रहे हो आप. इससे पहले आपने किसने कहा था इलेक्ट्रिक फील्ड, पोटेंशियल,
सर
बैरियर
मैंने
विड्थ, मैंने का
सर
नाम
उत्सव
सब.
कुमार, सर
हाँ,
उत्सव.
सर, और एक सिंपल टर्म है, मतलब आपने बिल्कुल सही डायरेक्शन में बताया, बट एक सिंपल टर्म आप मिस कर रहे हो. इफ द मटेरियल्स विल बी चेंज फ्रॉम emitter is suppose X material, base is Y material.
Concentration.
हाँ?
Doping concentration.
ना, डोपिंग कंसंट्रेशन भी हमारे हाथ में है, तो हम बाहर से ले करके ला रहे हैं. आप जब एक बार खरीद के ला रहे हो बाहर से मटेरियल, बट डोपिंग कंसंट्रेशन इज ऑलवेज फिक्स्ड.
सर बैरियर पोटेंशियल बोला था मैंने.
बैरियर पोटेंशियल बोला था, उससे पहले बैरियर पोटेंशियल उसका कॉज है.
बैरियर विथ.
बैरियर पोटेंशियल मेनली आपके फॉरवर्ड बायस और रिवर्स बायस से कंट्रोल हो जाता है मेनली. हाउएवर देयर इज अ स्मॉल टर्म व्हिच ऑल यू आर मिसिंग. एक ही चीज है बैरियर पोटेंशियल और पोटेंशियल ड्रॉप. कृष्ण के 108 नाम की तरह है, इधर का उधर. एनर्जी बैंड गैप. मटेरियल कैसे कैरेक्टराइज होते हैं? सिंपल मटेरियल, बिकॉज ऑफ देयर एनर्जी बैंड गैप. Why silicon is different from germanium? Germanium is 0.8 electron volt, silicon has 1.1 electron volt. That is the basic thing. If the energy band gap changes, then many other effects come into the scenario. So till now, whatever bipolar junctions transistor we have studied, basically those are homojunction bipolar transistor. That's why, because those are of same material, silicon. Now we would like to focus a little bit introducing different materials, emitter, collector, and base, so that it becomes a heterojunction bipolar transistor. क्यों जरूरत क्यों है? Let's come one by one. If you recall, मतलब ट्रांजिस्टर स्विच ऑपरेट करने के लिए हमें बहुत ज्यादा दिक्कत करने की जरूरत नहीं पड़ती, क्योंकि फॉर द स्विच टू बी ऑफ इट इज ऑलवेज जीरो, and switch to be on, manufacturer's date sheet dekh lo, or if you apply the mathematical equations, just push it in the active region, saturation region, so that the switch becomes on. The problem is always when the transistor is in the active region, always to make a stable active region operation or a stable amplification. Stable amplifications का एक सबसे important thing है, the emitter हम heavily doped तो कर देते हैं, but the designing of our circuit is in our hand, so that is heavily doped electron can shoot more and more electrons to the collector. Then only more and more collectors to be reached, and amplification will be possible through the V equals to IR, a linear relationship. बाजार से n plus emitter खरीदने से ही that emitter will only the emitter will inject more and more number of electrons to the collector. No one has ensured that you have to take care through your design. So the important part is how efficiently your electron is providing the your emitter is providing the electrons to the collector. And that's why the efficiency of the bipolar junction transistor depends on a term efficiency or injection efficiency, IEN, the electron component of the emitter current, by electron component of the emitter current plus hole component of the emitter current. Remember, this emitter comprises of both majority carrier and minority carrier. But if it is an NPN transistor, how much N-type carriers are reaching at the collector, that depends. And how less and less your minority hole current, which is actually flowing in the backside, that should be reduced down. Because if your IEP is reduced down, obviously your injection efficiency will be higher. What should be the efficiency of this kind of an efficiency, the maximum value of the efficiency? In any case, in
One.
such one, always in a probabilistic manner, the efficiency, maximum efficiency value will be 1. So your focus of the design should always be achieving an injection efficiency of 1. So the efficiency is limited by the fact that the carriers can flow from the base into the emitter region over the emitter junction barrier, which is reduced by the forward bias emitter base junction. फिर से efficiency is limited by the fact, limited why it is reduced, because base to emitter region में the electrons or the carriers can flow from base to emitter region, which actually contributes to this minority component. Over the emitter junction, the reason, अगर आप homo junction उसके sorry पुराने बेस एमिटर जंक्शन के आपने पढ़ा होगा, when we have drawn after the application of forward biasing and reverse biasing, forward biasing always reduces the barrier potential at the emitter base side and reverse biasing increases the contact potential at the collector base side. So automatically जब इसके barrier potential कम है, so this reverse flow of the carriers can happen easily, which is reduced by the forward bias emitter base junction, or that a lightly doped and narrow base region is required and a heavy doped material for emitter is also required. Those are the design precautions which already we have considered. However, the light doping and the narrow width of the base results a very high resistance. A very high resistance means there is always a restrictions in the flow of the current, which automatically affect the injection efficiency. Thus, for a high frequency operation with high efficiency, it is required for a BJT to have a heavily doped base but lightly doped emitter. What is the opposite of the conventional BJT? Very carefully, if you have taken lightly doped and narrow width base, it will ensure high resistance. High resistance means low amount of current, so low injection efficiency, amplification के लिए काम नहीं करेगा. So actually for a BJT design, or the practical one obligation is you have to have a very heavily doped base but a lightly doped emitter, which we usually don't take. And that gives many parasitic effects other than resistance as well. Yes, someone?
Sir, it is saying for high frequency operation. For low frequency operation, if we use that,
No, but a high
then
efficiency operation? Even if it is a low frequency, those two are different
efficiency
terms.
is what?
Efficiency we require everywhere, whether it's high frequency and a low frequency. That is
Means
another.
then why we're specifying that high frequency operation and that one?
I'm just specifying, later on we will come when we will come to the capacitive effect.
Okay, sir.
We presently only consider for the high efficiency operation. So this allows some different mechanism rather than doping to control the relative amount of injection of electrons and the holes across the junction. ये lightly doped, heavily doped, हम तभी कर सकते हैं when the dopings are different. Dopings, once we have brought it up, it is always fixed. In the experimental level, we cannot change the doping once it is fabricated. So some other mechanism we have to adopt. The basic adapting mechanism we have to taken care of by this heterojunction structure. HBT is made up of two different materials and having different band gaps, on contrary to the ordinary homojunction bipolar transistor, similar junction bipolar transistor. So it is quite look like in this way. Previously आपको याद होगा, when we are applying the forward bias emitter based junction, then only we are achieving this kind of a barrier width difference. Now from the very beginning, without applying any bias, forward bias, reverse bias in the emitter base and base collector junction respectively, just by the different materials we are taking, because different materials have a different band gap, so that's why we are taking this kind of a structure. So in the middle, that is in the base, we are taking certain higher band gap material, correspondingly different band gap materials in the emitter and collector, so that this potential difference should be some other color. Potential difference automatically comes into the scenario through the structure itself. So ECEV, the Fermi levels are different now. Heterojunction NPN, and capital N here means the N plus equivalent to P small n. The emitter, base, and collector are designed through this heterojunction bipolar transistor. What is the consequences of taking this structure? If you can neglect the differences in the carrier mobilities and other small effects, assume the temperature and everything is fine, so mobilities are also same. The carrier dependencies across the emitter is usually now governed for a heterostructure is IN by IP is doping of emitter by the acceptor concentration of the base, and one extra term comes. Previously, what was that? The IN, that is the electron component, and the hole component ratio is donor by acceptor, directly proportional tha. For the heterostructure, one extra terms will come, E into e to the power or exponential the band gap difference by kT. That one extra term comes in case of an HBT, heterojunction bipolar transistor. The ratio of the IN and IP is now proportional to the ratio of emitter and base carrier concentration. Additionally, in HBT, the ratio depends on the band gap difference EG. The band gap difference EG means in between the emitter and the base, because हमारा efficiency के लिए we are mostly concentrated on the emitter base ratio. Base collector is reverse biased, we are not that much bothered about that. So band gap difference, the wide band gap difference of A and the narrow band gap difference base appears in the exponential factor. Exponential factor always increases or decreases in a higher fashion. So relatively small value in the exponential factor can dominate so that we may choose heavily doped base to reduce the base resistance and a lightly doped emitter to reduce the junction capacitance. Delta EG is what? The difference between the emitter and base, or vice versa. जिस तरफ तुम higher band gap, lower band gap material लेना चाहते हो. Now, even if you can choose a lightly doped emitter and heavily doped base, you can reduce down the resistances, but that will merely affect due to its exponential factor. So basically, a high potential hill at wider emitter base band gap restricts the backflow of the holes to the emitter to reduce the IEP. So even without the application of the forward biasing, because forward biasing only reduces this potential height. But now structure wise, you have created a huge band gap. So what happens? This majority holes flow in the back side, because this is normal active mode mein. Majority holes of the backflow from base to emitter is restricted. If the backflow is restricted, that means this IEP term will become negligible. And what happens? IEN by IEF, the injection efficiency will be towards 1. That is the basic thing, a scientific thing for which it is being chosen. The high potential hill at wider emitter base band gap restrict the backflow of holes to the emitter to reduce the IEP, and hence the emitter injection efficiency increases, which was our preliminary focus. Materials commonly used in HBT is aluminium gallium arsenide system. That means aluminium gallium arsenide at the emitter, gallium arsenide at base and collector both. क्योंकि हम base and collector junction में उतना focus नहीं कर रहे, तो usually base and collector हम same materials ले लेते हैं या कभी different भी लेते हैं. System because of its wide range of lattice matched composition. Otherwise, indium gallium phosphide system, silicon germanium system. There are many such combinations which we have taken, which are basically different alloys and compounds which we have already studied in our last semester. So that is the basic concept of heterojunction bipolar transistor. Although the operations or the mathematical equations are exactly same, there is nothing any difference, but usually for the better design structure we take the heterojunction bipolar transistor. Yes.
सर आईईपी 0 कैसे हुआ, मतलब आप फिर से एक बार रिपीट करें सर।
यहाँ पे हमने क्या लिया है, पोटेंशियल हिल हमने हायर कर दिया है। पहले आपने पोटेंशियल हिल एमिटर बेस जंक्शन में क्या होता था, जो बैरियर पोटेंशियल होता था, ड्यू टू फॉरवर्ड बायस लो होता था।
यस सर।
फाइन। लो होने के कारण क्या होता था, जो मेजॉरिटी होल से एट द पी टाइप बेस दैट वाज अट्रैक्टेड टुवर्ड्स दिस पॉइंट।
तो
रिमेंबर,
विच पॉइंट?
from base to emitter side the holes were,
यस सर।
because this is forward bias.
यस सर।
फाइन।
यस सर।
होल्स फ्लो होते थे, होल्स अगर फ्लो
यस।
होते थे तो आईईपी का कंट्रीब्यूशन होता था, तो इंजेक्शन
यस सर।
एफिशिएंसी कभी भी 1 नहीं अचीव होता था, IEN by IEN plus IEP. Now,
यस सर।
due to HBT structure, we have increased this potential hill a lot. So, अगर आप फॉरवर्ड बायस अप्लाई भी करते हैं, ये पोटेंशियल हिल बहुत ज्यादा रिड्यूस नहीं होते हैं। पोटेंशियल हिल अगर रिड्यूस
ओके
नहीं,
सर।
so these hill holes from the base cannot go to this side. They are restricted by this potential hill. So
गॉट इट सर।
जितना कैरियर्स कम होंगे, IEP मतलब करंट उतना कम होंगे, so IEN will cut it down and it will give a injection efficiency bond. That is the thing.
यस सर।
Fine. So which we have taken in care of through these alloys and compounds. Very quickly before we leave, what were those alloys and compounds we did? Alloy or compound किसे किसे बोलते हैं? Those we have already done. That's why I'm asking.
सर alloys are mixtures of different elements और compounds तो chemical reactions से बनते हैं सर, different elements के।
alloy में वो नहीं होते।
सर वो mixtures होते हैं एक तरह के, कि वो उसके जो होल्स होते हैं वहां पे जाके अपना वो हो जाते हैं।
नहीं, क्या बोल रहे हो? What is an alloy? What is a compound?
सर एलॉय मिक्सचर ऑफ मेटल्स होता है विद सिमिलर लैटिस स्ट्रक्चर।
और बाकियों में आप वो कर सकते हो, विदाउट लैटिस मैचिंग कर सकते हो। लैटिस मैचिंग सब जगह जरूरत
सर
है
एप्लीकेशन पे डिपेंड करता है
ना। लैटिस मैचिंग तो हर जगह ही चाहिए। लैटिस मैचिंग इज बेसिकली अ बेस। आप लोगों ने कभी घर बनते हुए देखा है? खरीदते हुए बोल रहा हूँ, आजकल तो सभी फ्लैट में
यस
हम
सर
लोग रहते हैं,
देखा
पुराने घर।
देखा
तो
देखा
कभी भी जब कुछ भी डबल स्टोरी, ट्रिपल स्टोरी या 25 स्टोरी कुछ भी फ्लैट्स बनते हैं, क्या नीचे आपने देखा है गड्ढा खोदा जाता है या जमीन से ही बनाया जाता है?
यस सर नीम खोदी जाती है
तो
कम
अगर
से
आपने
कम 5 फुट
स्टोरी
गहरी।
बिल्डिंग बनाने की कोशिश की और सुप्रीत सिंह ने 25 स्टोरीज बिल्डिंग बनाने की कोशिश की, दोनों ही सेम विड्थ के या सेम लेंथ के गड्ढे खोदेंगे?
नहीं सर,
क्योंकि नीचे का
नीचे नहीं
बेस
विड्थ ज्यादा होनी
मजबूत होना
चाहिए।
चाहिए, so that it can withstand earthquake ना आए, anything. This is the basic concept of lattice matching. Lattice matching हर जगह ही चाहिए। Lattice matching अगर नहीं हुआ, proportion to lattice matching, whether it's an alloy, whether it's a compound, none of the device or none of the system will exist. They will break down. बनेगा ही नहीं, यही टूट जाएगा। चलिए अगले क्लास में डिस्कस करते हैं इसके बारे में। रोल नंबर 1,
Present, sir.
2, 3,
Present sir.
3, 2 दे दिया।
3 present sir.
Okay, 4,
Present, sir.
5,
Present, sir.
6,
Present sir.
7,
Present, sir.
8,
Present, sir.
9, 10,
Present sir.
11,
Present, sir.
12,
Yes, sir.
13, 14.
Present.
Is it 13 or 14?
13, sir.
14,
Present, sir.
15,
Present, sir. 15.
16, 17, 18, 17 present, 18. Okay, 18 present, 19,
Present, sir.
20,
20 present, sir.
21 present, 22,
Present sir.
23, 24 present. Oh, sorry, 23. 25 present. 26.
Present, sir.
27.
Present, sir.
28.
Present, sir.
29.
Present, sir.
30.
Present, sir.
31. Present. 32.
Present, sir.
33.
Present, sir.
34.
Present, sir.
35.
Present, sir.
36.
Yes, sir.
37. 38.
Present, sir.
39. 40 present. 41. 42. 43. 44 present. 45.
Present, sir.
46. 47.
Present, sir.
48.
Present, sir.
49.
Present, sir.
50. Or 50. 51. 52.
Present, sir.
53 present. 54 present. 55.
Present, sir.
Satyajit.
Present, sir.
Thank you. And very unfortunately, tomorrow I will also take class. सुबह सुबह आप लोग Republic Day मना लीजिएगा. So in the afternoon, as per the timetable, I will take the class. Otherwise, I will not be able to manage. Thank you. See you tomorrow.
Excuse me, sir.
Yep.
Roll
बताइए.
number 27.
Roll number 27 given. Manika.
Yes, sir.